In electricity and magnetism, there are a number of very important laws that all work together. We've already seen one of these laws back in chapter 16. It was known as Gauss's law, which relates the total electric field coming out of a surface to the total charge within the surface. We're going to look at a second one of these laws. This is called Ampere's law. Ampere's law relates magnetic field to some sort of a loop around a current. So here is how this works. You have a current running through some flat surface. You draw any loop you want. It can look like absolutely crazy. As long as it's a flat loop that goes along the surface. I should have drawn one. Maybe we could have done something like this. Some crazy loop that goes around your current. Well, it turns out that the total magnetic field that is parallel to the line you just drew times the length of that line is always going to equal mu naught, the permeability of free space, times the total current within that loop. Okay. So let's use a simple example for this. Let's just take a single wire and just do a simple circle around it. Okay. A circle with a radius r. Well, that means, notice your magnetic field. You can draw my magnetic field in blue. Your magnetic field is going to be a circular line that just goes right around the current, I. And so let me actually redraw this because my red line didn't look right. Basically, your magnetic field is always going to be parallel to the circle that you drew. So my magnetic field that's parallel to my line, which is the magnetic field itself, times the length of the line has to equal mu naught times I. Well, what's the length of my line? It's a circle going around, just a two-dimensional circle going around I, and the equation for the length of the outside of a circle is the circumference of a circle, 2 pi r. So if I solve for the magnetic field, then I get mu naught divided by 2 pi times I over r. And you'll remember from our last video that this was actually the equation for the magnetic field around a wire. This is where we got that equation, was from Ampere's law. Let's do another example here. Here we have a solenoid. It doesn't quite look like a solenoid, but let me illustrate what's going on here a little bit better. You have a wire coming down with current flowing that direction. It goes in and then comes out and then goes in and then comes out and then in and out and in and out and in and so on all the way through until it comes out the other end. So, all right, so I'm going to get rid of that just so that we can keep a clear picture of what's going on. So your current on the top is coming out through multiple loops of the wire coming out of the page. And on the bottom of this figure, we've got currents going into the page. Now to find the, to use Ampere's law for this, we're going to draw a loop, a square loop, like this. Okay. We're going to talk first about the first segment, A to B. Okay. Now, we want to know the amount of magnetic field that's parallel to the length from A to B. That's going to equal mu naught times the total. Here, let me, yeah. We're just going to do this first of all. B parallel to the length from A to B. Well, the length from A to B is just going to be L, but how much magnetic field is in this area? Well, all of your magnetic field is inside the solenoid, not outside. So my magnetic field is going to be 0. Okay. So this is A to B. Now if we go B to C, which would be this stretch, then we want to know B parallel length B to C. Well, its length is some length, whatever that is, but how much magnetic field is parallel to this? Well, there's your line, and there's your magnetic field, which means they're perpendicular to each other, not parallel. So we have no magnetic field that's parallel to my line from B to C. So again, that's going to equal 0. If we go C to D now, which is this stretch, and then B parallel LC to D, that's going to equal, well, now I do have a magnetic field that is parallel to this line in the same direction. And so that's going to be my magnetic field B, whatever its value is, times the length L of my loop. All right. Now we're going to do our last segment, going from D back to A, this segment right here. This is the same setup that we had going from B to C. There is magnetic field that's parallel to the line, but it is, sorry, there is a magnetic field around the line, but it's perpendicular, which means there is no magnetic field parallel to that line. There is no magnetic field parallel to that line. Okay, but this isn't just what is the B magnetic field times length of an individual segment. We want to know the total. So we add up all of those. Well, we just get BL. Okay, so sum of B parallel times delta L has to equal mu naught I enclosed. Well, that's going to be magnetic field times the length of your solenoid, whatever it is. What is your current? Well, remember that you have a current I going through here. And you have a current I going through here, and through here, and through here, and through here, so on, through each individual wire. So the total current would be your current I times N, the number of wires you have inside that loop. So the magnetic field of a solenoid then is mu naught Ni divided by L, where N is the number of loops and L is the length of the solenoid. And that's exactly the equation we got at the end of last video as well. So there are a couple of illustrations of Ampere's law. Let me come back here just to illustrate the equation one last time. Ampere's law says that the total magnetic field parallel to some loop times the length of that loop has to equal mu naught times the total current within that loop.